Our discussant will be Pierre Nguimkeu. Please take it away.
Thank you very much. Thank you very much for inviting me to this conference. I think I share the same view or opinion with Desiree, that the format is very interesting. I think when you think about having to present a paper with the authors in the audience, you read the paper a bit more carefully than what you do when you are a referee or just a discussant. So I read this paper with great interest, and it's a fantastic paper. And so the authors are trying to look at how we can improve the estimation of treatment effects, especially in cases where we have misclassification. So the discussion is going to focus around the fact that we can basically look at the impact of a treatment on an outcome on a linear regression framework, right? So this is a linear regression framework where the treatment indicator is the binary regressor, and we can think about this binary regressor as SNAP or food stamp participation, and we are going to fix our ideas on that particular treatment. There are various possible outcomes that have appeared in the literature: BMI, food insecurity. Today we are going to focus on diet quality as the main outcome of interest. Right? And there are two common issues when you're dealing with this type of models or problems. The first is that the treatment indicator is endogenous. So SNAP participation, there is a selection to the program, and so this is not an exogenous treatment. So that creates the first difficulty. So you will need instruments to be able to estimate such treatment effect. But the second complication is that treatment indicator is misclassified. That means people who receive food stamp report that they didn't, and people who didn't receive food stamp may report that they did. Right? So if you are just focusing on people responses, you are picking up the wrong information for your treatment effects, right? And so this further complicated, especially that even in the case where now you have instruments, you still cannot fix the problem. The measurement error in this case is a non-classical measurement error, which means the true value is correlated with the error, and so instruments, at least the classical ones, are not going to be able to solve it. So what do we do? So there has been a couple of approaches that are used to address this type of issues. We can group them into maybe 3 or more groups. Those approaches that use bounding, right? So you're just trying to bounce within a certain interval in order to have an idea of the magnitude or at least the sign of the treatment. And there are various papers around that. Those that use information about the misclassification rate, that paper, like paper by Kreider. There are other that use difference in inference. Desiree and Austin have a cool paper on that. It's still a work in progress, but it's a very promising paper that addresses misclassification in the case of difference in difference. Then you have some papers that try to do point identification using extra information, either using instruments or using some parametric model to jointly model participation and misreporting. And some of the papers that I wrote with Austin are part of this. Now there is this other approach that uses Bayesian inference, starting from a prior information about the parameters and trying to infer about the treatment effect itself. And so Martijn has a paper with Chris Bollinger on that. And the current work is going to take it from there, right? This work is going to take it from that last line of the literature. And so what is this paper doing? This paper is trying to fill 2 gaps. The first is that the bounds that we have in general in practice are too wide and uninformative. So you think about bounds going from negative values to positive values. So 0 is in there, we don't know whether it's positive or negative. So it doesn't tell us much. We don't know whether the size is big or small because the bounds are wide. And so we are not learning much from these traditional bounds. So how do we improve on that to be able to make sense? And so there are three ways basically that I think about. They say, well, if you have information about the outcomes, maybe you know that the outcome is bounded within a certain range, you can include that information in your bounding exercise and potentially narrows the bounds. Or maybe you have more information about the nature of the distribution of the outcome. Maybe you know that people who are treated are more likely to have positive outcome than people who are not treated, things like that. And so you add additional information or assumptions in the form of monotone treatment response. I'll talk about that later on. And then you are able to narrow the bounds in a way that it becomes more informative. So that's the first gap. The second is to say, well, now that I have the possibility of bounding in a very narrow way, these estimators or these parameters, maybe I can use it as a prior information in the Bayesian inference to be able to get some posterior distributions that are more informative as well. Because the typical approach that Bayesian people use is that they start with an uninformed prior. And usually that might lead you to distributions that still doesn't give you as much information. But now we have an extra information coming from the bounds, so maybe we can incorporate that into the Bayesian inference and improve the estimation, right? And so that's what they do as well in the context of this work. And by doing that, they extend the paper by Chris Bollinger and Martijn in a way that allowed to incorporate two important aspects. The fact that you can use any amount of exogenous regressors in the model, and also the fact that you can improve on the prior distribution, even looking at the average treatment effect itself. And so just to give you have a view of the result before I go into the details. So they are able to show that we can obtain narrower bounds by incorporating existing information, either in the form of the distribution of the outcome or in form of some monotonicity assumption that you can incorporate in the framework. They are also able to show that you can improve information about parameter bounds if you use these bounds in the Bayesian framework. And they apply it to the food stamp and diet quality, and they are able to find a small negative effect on the average treatment on the treated in this particular application. Now I'm going to tell you about the model and the methods, about the data and the results, and finally I'll give some comments about their work. So this is the typical model. It's a linear regression model, very simple, where the objective is to estimate beta. The problem is that X star is not observed because X star is the true participation, but we don't observe that in the data. The data only shows us a surrogate that is misclassified. So the surrogate is X, and X is misclassified. And you can think about two types of misclassification. False positives, where people who didn't participate report that they participated, and false negative, people who participated report that they didn't participate. P is the proportion of false positive, Q is the amount of the proportion of false negative. And we are going to make the simple assumption that the sum of these misclassification probabilities is less than 1. Now, this assumption is not restricted at all. It basically just says that we are going to assume that the proportion of true tellers in the data is bigger than the proportion of liars, right? Now, if you believe that is the opposite way, then just take the opposite of the responses, and you will be back to the same case, that the proportion of true tellers is bigger than the proportion of liars, right? So this is not a restrictive assumption at all. The objective here is to estimate beta. Now, boundings is a way to go through, and we are going to start by looking at the case where participation is exogenous. So this is a very simple case, and this is not very common, especially in this type of application, but let's start with these two fixed ideas. So B here is the OLS, D is the OLS of X on Y controlling for all the regressors. And what Bollinger showed is that you can basically bound the treatment effect between the OLS and a convex combination of those two quantities. And in that case, the sign of the treatment effect is known, right? So the sign of the treatment effect is the sign of the OLS. So you know the sign, and you're just worried about the size of the effect. And so these are the bounds that were basically proposed by Bollinger. Now, in this paper, what they say is that, well, in this case, you can exploit information about the distribution of y and say, if we know that y is bounded between two values, like for example, we are talking about die quality here, it ranges from 0 to 100, we know it's bounded between 0 and 100. We can incorporate that and get something that is a bit more informative or narrower than the Bollinger bound. So this result is true, and it's very cool. And we'll see that in the data, this is actually showing up, right? So we are able to narrow down the bounds. The more complicated case and the more common case is the case where we have endogenous participation, right? Now, if you have endogenous participation, things are a bit more complicated. We are going to look at these three parameters, the parameters of interest, average treatment on the treated, average treatment on the untreated, and the true participation probability. In this context, we can still bound the average treatment effect this way, but unfortunately, this coefficient and these coefficients are unknown parameters. They can be positive or negative. It's very difficult to pin down their sign. And so in practice, as you will see, it ranges from negative values to positive values, and the interval could be quite wide. So we are not learning much from that. So what can we do? So we want to be able to improve on that. And so we start making some few assumptions based on the type of data that we are using. So the first assumption is the monotone treatment response, not monotonous, okay, and which basically says that for everyone in the population, being treated is better than not being treated. And I'm going to look at the case where this covariance is positive. So in that case, with this assumption, we can narrow down the bounds a little bit. So what has changed here is just this lower bound where now we have a proportion of the OLS. Right? So mu x is the probability of observed participation. So the lower bound here, it is improved. And so these bounds are tighter than the previous bounds. If we make an additional assumptions about the monotonous treatment effect, meaning that the expected outcomes of participant is either bigger or lower than non-participant, then we can further narrow down the bounds. So you can realize that these bounds are narrower than this bound because mu x is a probability, so mu x is lower than 1 and positive. And so these bounds are tighter than the previous cases. And so with this additional information, we are able to narrow down the bound, and more importantly, we are able to identify the sign of the treatment effect. And so this is a summary of the finding in the boundings. And so this is the ones that are unidentified, neither in sign or magnitude. But then when we start adding these assumptions, we start getting things that make more sense. So B is the OLS. So if we know the sign of the OLS, we basically know the sign of the treatment effect. And so MTS and MTR, when you add these two assumptions, you get this bound. So these are the best bounds that you can get at this point. Now, if you add also the fact that the outcome is bounded, then R is also comes into play because R is the range of the difference in the two potential outcomes. Now, the other approach is to use Bayesian inference. Right? So I don't know much about Bayesian inference, but I'm just going to tell you the way I understand it from this framework. So the first thing is, notations, right? So what you have is the data, the outcome, the exogenous regressor, and the observed treatment, which is misclassified potentially. Now, what you can compute from this data are sample statistics. You can compute the mean, the variance, the covariance of all these values, right? And so these are what we are going to call phi, which are the sample statistics. You can observe this and identify them from the data. The parameter of interest are these ones. We don't have them. We don't have the misclassification probabilities, we don't have true participation probability, and we don't have the various treatment effects. But with analytical relationship among them, we can reduce the dimensionality of the problem, either this misclassification probabilities and average treatment on the untreated, or misclassification probabilities and average treatment on average treatment effect. So this is where inference is going to take place. And so Bayesian inference is going to proceed by computing the joint distribution of lambda, which is our parameter of interest, and sample statistics, as posterior that can be decomposed in as in terms of multiple priors. Now, the interest of this method is that these priors are going to use information about the bounds in such a way that we have informed priors. And so that inference becomes more informative than what you do usually if you don't have any additional information. And so you will start by estimating the parameter that computes the sample statistics using a semi-parametric approach. And this is also a contribution here because typically what you do is you make assumptions about the parameter, the distribution of the model, maybe assuming that this is normal or stuff like that. But here, they relax that assumption and say, well, we are just going to let the data speak for themselves. We are going to use a non-parametric approach by constructing support points based on moment conditions. So there is no parametric assumption here apart from the fact that we are just using moment condition. Moment condition means that the population mean is equal to the sample mean, things like that. And so this is non-parametric, and it makes that the approach itself is semi-parametric. And once we get that, we are going to sample the values of interest based on our conditional prior, right? Based the prior given the first draw that we had. And from there, we can obtain our inference from the sample of the draws based on other assumptions that we can make. For example, we can think about these classification probabilities in a way that reflects what we see in the data. For example, papers by Meyer and Coulter shows that in the case of food stamps, we can think about false negative as being as high as 50%, whereas false positive rates are less than 1%. This is because typically food stamps, there is a stigma attached to it. People are more likely to report that they are not on food stamp, although they are. But very few people report that they are on food stamp when they are not, right? So in the data, we do see that false negative rates range from 23%, if I remember, all the way to 50% on various household surveys, whereas false positive rates are very, very, very low. And so you can exploit that information as well in the Bayesian inference to be able to get a more informative results or estimations. And so we are going to use that, and we are going to also we are going to report the results of this estimation. We are going to also examine the probability that beta 1, the average treatment on the treated, is smaller than average treatment on the untreated, because this is going to tell us whether the MTS or how the MTS assumption is holding in the data. Now the data is from the NANES survey, the National Health and Nutrition Examination Survey, ranging from 2011 to 2017. And it includes information about ethnicity, age, household composition and size, education, income. The diet quality, which is our outcome of interest, is going to be the healthy eating index, which measures the adherence to the federal dietary guidance on diet composition. So this is composed of 13 components, and the scores range between 0 and 100. So we already know from here that scores are bounded. SNAP is the largest USDA food assistance programs. It covers about 42 million populations per month, and it's a huge in terms of expenditures, right? So that also warrants why studying this is important, at least for policy. The sample that is considered here is a sample of eligible household, which means that their income needs to be smaller than 200% of the federal poverty line. And based on this sample, this is what we have in terms of summary statistics. We have SNAP participant, SPAN non-participant, and then we have various personal characteristics, ethnicity, gender, marital status, education, household income and size, and we have the index, which is our outcome between the two groups. Now, if you look at the bounding approach that we first considered, you'll see that if we don't make any assumption, this is the bound. The bound goes from negative 100, which is the minimum we can get, to 86.9, right? So what what can you say about this? There's not much you can say. You cannot say anything about the sign. You cannot say anything about the significance. Now, if you start adding assumptions, like the MTR assumptions, now it narrows to this. Although this is still white, but at least we have a sense of the sign, right? We know it's negative. Same when you look at these two, right? So we start seeing that this is negative. So as much as we start including these assumptions, you start having at least an idea about the sign of the treatment. And so what we can conclude here is that adding these additional assumptions at least allow us to get an idea of the sign of the treatment effect, even if the magnitude itself is still a bit uncertain. Now for the Bayesian estimate, the estimation is going to look at the average treatment on the treated, also on the average treatment effect, the average treatment on untreated. And in all cases, I'm going to show you summary statistics, including a 95% high probability density distribution. And so I'm also going to show you the proportion of negative MTS in the data. Now, this is the first one, which is basically looking at inference on the ATT. The green line is uninformed priors on misclassification probabilities. And as you can see, it's quite expanded. But when you start making more assumptions, like having truncated normal, where the truncation is based on the bounds on the misclassification probabilities, now you start seeing more concentration of the distribution, right? And so that means this information is useful to narrow down the distribution of the average treatment effect here. The summary statistics here shows you that the 95% confidence interval shows a negative sign. And once you start including more assumptions about the prior, you start getting something more narrow, right? So 25% quantile is -5, 75% quantile is -3, so you start getting something a bit more narrow as you start including the additional information on the priors. If you look at the average treatment effect with prior information about the average treatment effect on the untreated, then this is the distribution you have. You can have various priors. I'm going to look at the priors 1 and 3 are priors that puts more uncertainty about the average treatment effect on the untreated, and you can see that the distribution is wider. But when you start putting more structure on the prior, it concentrates more around the expected values. And so, but even though it concentrates, you can still see that we still have uncertainty about the sign, right? It's narrow, but it still goes from negative to positive, right? So we still have a bit of uncertainty about the sign of the average. It's going to be the same for this case where you're still looking at priors on beta 0, but at the same time, you are changing the structure of the misclassification probabilities. You're allowing them to be truncated, both of them to be truncated normals. And the same scenario or same pattern happens here. With more uncertainties, you have wider distributions, but with more structure, you have a more concentrated distribution. However, you still have uncertainty about the sign, although the bounds are narrower. The last scenario is when now you impose in your prior that the average treatment effect is positive, right? So in that case, you have this prior, and for the positive case, you will see that the line, the associated line, so the red line and the black line, are shifted to the right, and so now you start having estimations that shows a positive distribution here. And in this particular case, you can see that the average treatment effect, at least for these two last cases, is positive. Although for the former cases, it's still within negative and positive sign. So this means that there is still some amount of uncertainty about the average treatment effect. Although for the average treatment effect on the treated, we know from all the result that we have that it's going to be negative, right? And so just to summarize their contribution. So There is improvement in the bounds when you use additional assumptions in the form of monotonicity or the distribution of the support on the outcome. And they are able to show how to improve inference. That extends Bollinger and Martin's previous work in various directions. You have better informed priors, and you also have more flexibility, which incorporates other covariates. And then they are able to find small effects, negative and small effects on average treatment effect. Now, I'm going to give you the benefit of these methods. Right? The benefit of the methods, there are three types of benefits. First, you end up with narrower bounds, which is what we want when we are doing bounding. And then you have identifying sign, right? So we know the sign of the average treatment, at least in our simulation, we saw that we were able to identify the sign of the average treatment effect on the treated. In theory, we can identify the sign of the average treatment effect as well, as long as this assumption are satisfied. And then we also have a very flexible model where you relax the distributional assumptions and you can use a semi-parametric approach. And at the same time, you can incorporate various exogenous variables. Now, what are the costs, right? When there is benefit, usually sometimes there are costs. What are the costs? So the first cost is that there is an assumption that says you will assume that conditional on the regressors, the potential outcome of the untreated is going to be independent of the treatment, right? You can think about this assumption as being arguably strong, especially in the case of SNAP. And so, but this assumption is needed to get the signs that we are looking for, right, to identify the sign. But in the next slide, I'm going to talk a bit about how this assumption can be relaxed, because I think we all agree that in the case of SNAP, this could be strong. The MTR assumption is also costly because it imposes a direction or a ranking on the population, right, in the full population with probability 1, right? So maybe we may want to relax it a little bit, looking at, on average, whether it is the case, and I'm also going to discuss that as well. The cost, the computational cost is usual in this literature. Whenever you are doing semi-parametrics, you know that you will need more computer burden. And so the question is, does it perform well if W is large? W is a set of exogenous regressors. Should we worry about the cost of dimensionality as usual? So this is not typical to their work, but this is just the type of question we ask ourselves when we are doing semi-parametrics. So now, can we weaken the assumption of MTR? Well, I think maybe we can, because it seems like we can just focus on this assumption rather than the assumption on the whole population itself. Maybe if we just assume that we have either this or this, we might be able to get to the same result, right? This is something to look at, right? So if this is the case, then that will allow more applications because the assumption is less strong than what it is right now. The other question is, can we relax? Can we identify the sign of treatment effect without the assumption on selection bias, right? Well, maybe we can, because if we assume that there is selection bias, this is our new situation. What we can identify is the selection bias and the average treatment of the treated. Now, it seems that with the MTS assumption, we can identify the sign of tau 0. Right, based on whether it's negative MTS or positive MTS. And in some cases, we should be able to identify the average treatment in the treated, especially in the cases where this sum is positive, but we know that this is negative, right? That will imply that beta 1 is positive. And also in the case where this sum is negative, but tau 0 is positive, that will imply that this beta 1 is negative. In those cases, at least, we should be able to identify the sign of the average treatment effect, average treatment on the treated, and also the sign of the average treatment effect and average treatment on the untreated in those specific cases. Okay, so to summarize, the paper makes significant contributions, both theoretically and empirically. The empirical findings are potentially very important for policy because we are talking about a very huge budget here and a wide fraction of the population. And the theory potentially can relax to include more potential applications, right? Not just focusing on SNAP or that quality, but if we are able to relax some of this assumption, I think the paper has the potential to accommodate a wider variety of models. And I'll stop here. Okay.
Now for our author.
Let's try to see what I, or somewhere here as a tab.
Oh, we do that. Is that it?
That's
Right?
it, yeah.
And then we'll go Control L, I think it is.
Okay, thank you. All right, good morning, everyone. I am not Christian. I am Martijn van Hasselt. Thank you to the organizers for including our paper. Thank you to Pierre very much for very careful reading of our paper and really useful comments and thoughts. And I should say, well, a couple things. This is us, not the USDA, but we're so I wanted to put that disclaimer up. But so one of the reasons for us to kind of try to submit this paper here and fortunately have it be included in the program was that we've been working on this for a while and we've been kind of struggling with a way forward because we do multiple things. And one of the questions we've had, and we'd love to hear your thoughts too, is whether we try to do too much. So we have, as you probably sense from Pierre's discussion, there's part of the paper that very much goes into bounding exercise and kind of layering different assumptions and seeing how that affects bounds. And then there's part of the paper that says, well, okay, can we then use bounds, whichever you find acceptable, into a Bayesian prior and then see how we can do Bayesian inference without the usual sort of parametric assumption. So that's sort of a slightly separate part. So it raises the question, in our minds at least, whether we should really split this up into two pieces to kind of make it, more maybe a little cleaner. One thought, maybe a methods paper that splits off the first part versus a snap paper with hopefully a pitch for using Bayesian in that case. So that's an issue we thought about. To Pierre's point, that I'm so glad you picked up on it, and it's something that sort of, I wouldn't say pushback. Well, pushback. An issue that people have raised that have looked at the paper is this issue of selection. So in the way we formulate our model, and the way we sort of work with the bounds, we allow for selection based on the gains to treatment, but not for selection on the no treatment outcome, as you noted. So, we have this sort of usual decomposition of the difference between two conditional means, which is the ATT plus selection bias, and in a way, we assume that selection bias, we set it equal to 0. And the issue then that we have, and I think we have to work with Pierre's proposed solution, is that currently in the model the ATT would be identified if it were not for misreporting, right? And so then misreporting sort of becomes the only problem, which makes it which makes the range of applications limited. So we recognize that, and I think we're going to go down that path of including a selection parameter into it. I think that's a great suggestion, but it adds a parameter to the model, and so we want to think more about, can we bound it or not? Does that make sense? What would be a reasonable prior for that? So I think that's a work in progress, but I think that's one direction we want to take it. Now the other, and this is not necessarily something that came up in your discussion, but this again something we've sort of thought about, was instruments versus no instruments, and the goal of our paper has been to really provide an hopefully attractive approach when you don't have instruments, right? And it's not perfect, but now so we have sort of two alternative ways. One, someone might say, well, use instruments, even though they might not be perfect. Is that maybe a better way to go? Well, what if the exclusion restriction fails? So we have these two competing approaches. One that might allow for a, possibly invalid instrument versus, a bounding approach that uses no instrument. And so how does that sort of compare? So I think, that's in our minds a bit of an open question. The other thing that I think we haven't done yet, but I think would fit into a bounding paper would be to talk about monotone instrumental variables. So as Christian can tell you probably much more about, a lot of these assumptions that we entertain, whether it's about selection or MTR, may not be very palatable or very acceptable to people in the SNAP context. And so MIV is one that we haven't looked at yet, and is something that we probably want to consider. I think that's it. I wanted to clarify one thing, or at least this probably wasn't very clear from the paper, and I think we need to do a better job explaining it. But our Bayesian approach doesn't rely on the various assumptions, but what it does is it provides us with a way to kind of use those assumptions and build them into a prior. And so some of the results that Pierre showed and some of the results we have on the paper, they're not contingent on assuming MTR. You can build that in and then you would get some different pictures, or you cannot if you don't like it. The other thing you could do is you could incorporate a mixture of these assumptions. Makes it more complicated, but maybe you want to put a small weight on it just to allow for the possibility that it's reasonable. So that's another reason why I think the bounding exercise is somewhat independent of the Bayesian approach. So I just wanted to clarify that our Bayesian inference approach is not predicated necessarily on assuming anything something all the time. So anyway, let me leave it there. Thank you again, Pierre. This was great.
So I'll introduce our last student volunteer, Margarita Kwan. Please step up. Margarita's in the economics department and will be on the market soon. 5 words or less about you.
Hi, my research is mostly in moral hazard in health insurance, and I particularly look at Medicare population, and is interested how the decision about initializing treatment sort of depends on when the person was diagnosed and if a person becomes less myopic as they learn the structure of plans.
Thank you very much.
So thanks for
This,
So you should talk to Cecilia about this.
I did,
Okay, there you go.
Enrique.
Sounds about right.
Only ex ante allows.
So I have a question, and it's kind of like probably my misunderstanding of the Bayesian framework. So you have like an average treatment effect parameter, if you wish. Here now you take the mean of your beta parameter, and so should I interpret this mean exactly as I should interpret like an average treatment effect? And it goes to my second question. You not only have the mean, you have the entire distribution of this beta parameter. Like, what else can we learn from that parameter? How should I interpret? Because at the end, you take the mean, and I'm tempted because I'm frequent is to think that that's equivalent, but you have the whole distribution, so you can actually potentially answer more questions. How do I interpret this distribution of beta, or how do I map it to my understanding of, can we learn something other than the mean or something like that from that beta?
Sure, that's a great question. Thank you. So some of the graphs you saw, it's the posterior distribution of the average treatment effect. So even though you see the distribution, and it's tempting to sort of think of that as a distribution of effects, but rather it's a single parameter, so it's always the average, right? But it's plotting the posterior distribution for that parameter. Okay. So if we wanted a different treatment effect parameter, we would have to
Model something different.
And we'd still get different graphs, and there would still be distributions. But yes, that's sort of the way to think about those. It reminds me too, I'm sorry to use your question as sort of a jumping off point to another thought I had, was that some folks have told us that this is a story about treatment effect heterogeneity, like which we at the moment focus on these three parameters, ATU, ATT, and ATE. But maybe it's cleaner to just say, well, we're just going to look at one, or maybe someone would like to see another one, right? So that's also kind of folded in there. How do we deal with heterogeneity? Do we just, kind of present a whole bunch of them, or is it cleaner to just pick one and move forward? So again, it's been an internal struggle. So
Because you have the mean of the average treatment, but you also have the whole distribution. You can think about other like cutoff points and think about like what you learn from them.
yeah, I mean, in this sort of partial identified world, you'd have to rethink the bounds in that case too. So if you're then trying to focus on different parameters, your bounding exercise would look different, right? But it's certainly it's a good question, and there's certainly other parameters we may want to look at in that model, but we haven't done that yet.
I think yeah, you're trying to answer my question already.
Oh, okay.
So yeah, if I look at partial identification and Bayesian approach, for me, I would expect to see the distribution of the lower bound and distribution of the upper bound, right? Not the mean. Like so, each bound is like a random variable in the Bayesian perspective, right?
That's right. That's right. Yes, and this is also probably something I should or we should say in the paper that, and we didn't do it now, but we can certainly do this. We can estimate the lower bound and the upper bound, and then give a graph of that. So that's in the background. We just haven't reported it, but we then combined that with the prior to go to the parameter that we're interested in. Yeah.
So the next question is about the monotone treatment response and monotone treatment selection assumption. So I understand that in the frequentist world, the Mansky world, it's like the Y1 is bigger than or equal to the Y0. But when I think about Bayesian, you probably use the probability that Y0 be bigger than Y1 is equal to 1. But you can also allow it to be like 95% instead of 1. Mm-hmm. And see how that's kind of changing the bounds.
That's a great point. We've done that in some previous work, and then we decided to abandon it because we felt like that's a great point that you have this ability to work with these assumptions not with a weight of 100%, but maybe a little bit less and see what happens.
Okay.
Yeah.
Thank you.
Thank you.
I think this is outside the scope of this paper, and I apologize for that in advance, but is there reason to suspect that the treatment effect for the people who said they were on food stamps would be different for the people who said they didn't? And would that contaminate your results?
I think that's a great question for Christian.
So would the treatment effect be different for those who misreported as opposed to the?
Yeah, that's a great question.
So
that would get us into the world of sort of the differential misreporting, which is not something we kind of assumed away for now. It's a great point. I don't know if there's any work on that or.
No, that's a great question.
Yeah, thank you. That's.
I think a lot about, I work a lot with survey data, and I think a lot about administrative data where you can actually confirm the misreporting. Is there anything you can do here, maybe not with SNAP, but with some other outcome where people misreport and then you can use the full information to sort of assess the misreporting and see how well you do?
Yeah, so we have, that's a great point, and I think a lot of work has taken that route. What we do for this paper is we've used some of the documented misreporting in SNAP coming from Meyer's work and sort of assumed that used it to really inform our prior. So, he has a set of estimates ranging across a number of surveys, and even though we don't do that administrative matching exercise, we use his sort of statistics, his results to sort of inform our prior. But so that sort of actual working with validation data is not part of our current project, but it's certainly something that others have done. And I think Christian, you're
So one of the things is some of the the work on administrative data works on totals. So they might have total months reported on SNAP or total dollars. And that turns out to be very different than using administrative matches to survey records like microdata. But it's a really interesting question. It's unfortunate, but NHANES is not linked to our administrative records, so.
Thank you. So I just wanted to say a word about the alternative. Can you use the instrument? I think you're right about your suspicion that you might not have exclusion restriction, especially if you're in a standard framework, because here you have a measurement error on a binary variable. And so whatever is correlated with the treatment must be correlated with the measurement error. And so if you are running a regression model where you basically use what we usually call the operational regression, the error term will contain that measurement error. And so if you're using the instrument in a typical way, that instrument will be correlated with the treatment, but at the same time, it must be correlated with the measurement error. So in that case, you want to be a bit careful about the way that you're going to frame the model so that you can actually exploit the instrument.
Thanks for the great session.
All right, so that brings today's proceedings to a close. So thank you very much, Desiree. Thank you, Shu, and thank you, Pierre, for just fantastic comments. So just really, really, really well done. I remain grateful for our hosts, John and everybody in the back of the room for USC who's made today happen. And Daniel, thank you so much. Aaron tells me that lunch is ready and outside, and I won't blabber on too much because I know people have like flights to catch and things. But one last plea is that in the back, there are still some Stata cups and some swag and some snacks that are unopened. If you are local, please take all of it. It's gonna help make everybody's life easier. And next year, we hope to see as many of you as possible in either New York or DC. Deliberations are still ongoing, but more to come on that. Anirban.
Just wanted to thank Matt for organizing this.